First, you shouldn't have what's called multi-collinearity. That is, your predictor variables should not be too alike. The reason for that is this. I mentioned this a couple times before. What you get is you get regression coefficients. What do they say? They tell you something about the net benefit of this variable, given that I have all the other ones in there already. If I look at the net benefit of this variable and I have 27 other ones in there that are closely related to this one, then the net benefit of this single one is close to zero, and you get nothing. So it may appear like all these 27 variables have no effect whatsoever, but the only reason why I find this is simply because you add them all together, because then the net benefit of each and every one of them is close to zero. Okay, let's see. So this is what it is. Multi-collinearity is a strong correlation between two or more of the predictor variables that you use, and you don't want to have it. What do you get? Well, you typically see that these predictor variable, the coefficients, the estimated coefficients, tend to go to zero because the net benefit of any single variable is not that high. This is more an experience thing. What is called bouncing betas. Your estimates for your coefficients can change dramatically if you leave out one or the other variable. So what you typically do when you run a model, you try with a variable in there and another one, and then you look, okay, let's try this other one here. If now all the results are completely different, this is what's called bouncing betas. Your coefficients are dissimilar all the time, and that's also very often suggestive of the fact that you must have two or perhaps more variables in there that correlate quite a lot. Okay, how do we find it? Well, two ways to do it. One is simply to look at the correlation matrix of all the predictor variables. So if I have a big set of predictor variables, or a small one, let's say 10, I look at the correlation of all 10, and I check, do I find any high correlations in there? If you do, this is a recipe for trouble. I'll show you an example in a minute. And the second one is you calculate variance inflation factors. That's a new thing after running the regression. And these two things will tell you if you are in for this or not. And what can you do about it? Well, let's suppose that we have correlation between just two. Let's say a correlation of 0.99, so really high. This simply means, statistically speaking, this one and that one are the same. So there is really no need to include them both, and the simple cure is you get rid of one. Or you average them out and you add that one instead of the set of two. It didn't make any difference to begin with to include one or the other, so that's the standard solution. Matters are a bit more complicated if you have correlation between more than two, so it could be that 1 and 2 together correlate very highly with the third one. That's more difficult to find, but generally what you have in there is two variables that for some reason or another correlate too highly. Let's see how this goes. First, the easy bit, checking correlations. So here are the predictor variables that I use for the wine predictions, the vintage, the rain, the degrees, and more rain. And you see here that all these correlations are, well, let's say 0.27 in absolute value or less. That's usually nothing to worry about. So then the question is, okay, when should I start to worry? And the standard answer is, it depends. It depends because the more cases you have, the better you can get away with high correlations here. This is, if you have a huge sample, thousands and thousands of cases, then even large correlation between predictor variables can be disentangled. But in general, there is reason to check, let's say, if there are correlations above 0.8. And above 0.8, I mean above 0.8 in absolute value. So minus 0.9 is also above 0.8. Then you have to check. Might be that there are two values in there. For instance, here you could have thought that, for instance, the rain in the winter and the harvest time is probably related. Well, apparently it isn't. Only 0.27, so nothing to worry about here. That's the first thing to do. And the second thing is to look at these variance inflation factors. Here I ran the actual regression trying to predict the price of the wine, and then I typed afterwards the command VIF for variance inflation factors. You get a list of variance inflation factors back, and let's see what that means. Now, let me first give you the rule of thumb without knowing exactly what's going on. There are a couple of things to look at here. If you have one high value in there, in this 50 high means, let's say 10 or higher. Double check if there's something in your data where you have two variables that are actually measuring the same thing. Or if in general they are all highish, let's say 2.5 or 3 or higher, that's also a reason to double check what happens if you would exclude one or two of your variables. And in fact, these numbers here are estimates where you compare how wide these confidence intervals would have been if there would have been no correlation between your predictors. Doesn't really matter so much. The easiest thing is to just remember where to look for. And the standard thing you typically encounter if you are in trouble is one high value. So that would mean, in fact, let's say if there's a 10 over there for degrees, that would say, well, degrees is related to some of the other variables here. And if it wouldn't have been, then the confidence interval that you have would have been 10 times smaller, which is kind of a large difference, and that is suggestive of the fact that there's something going on here. Okay, so that's the way to look at correlation between predictor variables, and immediately one exception, and the one exception are categorical variables. We have a categorical variable, we create dummies, 5 categories, 5 dummies, we include 4, and these dummies by definition correlate. Can't help it, because, you know, when one is 1, and the other ones are 0. So there must be correlation between the two, and the only exception to the rule of excluding variables that correlate too much is with these dummy variables. These you want to have included all. So all as a set, or none of them. But not let's leave just 1 or 2 of these 5 out simply because they correlate too much. Okay, so predictor variables not too much alike, because if they are, then you know all your results are messed up, and you get also less significant coefficients than you would have gotten if you would have gotten rid of the problem. Okay, that's only the first one.